Hi class. In this lecture here, we want to begin talking about applications of differentiation. And so in this set of lectures, what we're going to do is we're going to study a ton of applications of the derivative and what it can mean when you want to analyze a function. And one of the first things we're going to look at is what's called extrema on an interval. And what you'll notice in the coming lectures, in the coming sections here, every single problem, every single application that I introduce is going to build off each other. So this concept of extrema on an interval is going to keep coming up in every previous or every subsequent lecture from here. So very important to understand this concept here. So what I'm going to do here is I'm going to introduce, in this lecture, I'm going to introduce the concept of extrema on an interval, and then I'm going to end up doing a ton of examples for you at the end of the lecture, just how you find it and what exactly it is. Okay, so what we're going to do in this section. So first off, we're going to understand the definition of extrema of a function on an interval. And one thing I'll say about this is when I give the definition for this extrema of a function on an interval, it's going to be really wordy. And then at first you'll be like, oh, I'm not really sure I understand what's going on here. But then after you see me do the first example of extrema on a function, you'll be like, oh, okay, this makes sense. Then I'm going to understand the definition of relative extrema of a function on an open interval. And then I'm going to spend a lot of time, I'm going to do probably 5 examples here of how you find extrema on a closed interval. Okay, so let's start with the definition of extrema. So let's let f be defined on an interval containing some value c. So we have this function f, and it's defined on some interval from a to b here, and c is somewhere between a and b. Okay. F of c is a minimum of the function f on the interval I when f of c is less than or equal to f of x for all x and I. Okay, so think about what this means is basically you're going to look at the graph of the function, and you'll see this in the first example, and we're going to look where is the minimum value of the function. Now f of c is a maximum of f on I when f of c is greater than or equal to f of x for all x and I. All right, so here again, what we're going to do is we're going to look at the graph of the function in our first example here, and we're going to say, okay, where is the highest value of the function? So I'm going to show the visual of this in the coming slide. So this will make more sense when you see the first visual. Okay. Visual on coming slides. All right, so a little bit more here. The minimum and maximum of a function on an interval are what are called extreme values or extrema. Okay, the singular form of extrema is extremum, but so we're looking for these what we call extreme values or extrema of the function on the interval. So the minimum of a function on an interval are also called the absolute minimum and the absolute maximum, the min and max there, or you can sometimes refer to them as the global min or global max on the interval. All right, so extrema can occur at interior points of the interval or at end points of the interval, and you're going to see this on in the coming slides. So more in coming slides here. All right, so extrema that occur at endpoints are called endpoint extrema. All right, so this will all make sense here when you see the first example I'm going to walk us through. Okay, so we have something then what's called the extreme value theorem. And it goes, if f is continuous on a closed interval from a to b, then f has both a minimum and a maximum on the interval. And so the extreme value theorem is a existence theorem. It just says something exists, doesn't tell you how to find it. But there's no way you can draw a continuous function on an interval from a to b such that it doesn't have a minimum and maximum value. There's no way to do it. So this extreme value theorem will hold. So I just wanted to quickly introduce this because some in subsequent lectures I might say via the extreme value theorem. Okay, so what exactly do I mean here then by this minimum and maximum? All right, so let's work an example here. All right, so let's consider this function. So let's consider the function f of x is equal to x squared minus 1 on the interval. So we're going to look first at the closed interval from -2 to 3. All right, and then what I want to do once I do this, I'm going to do the visual over here, is I want to find the extrema on the closed interval. So I'm going to just quickly sketch this, right? If you plug in 0, you get -1. You plug in -1 and 1, you get 0 in the function here. You plug in -2, you get 3. You plug in 2, you get 3. And then when you plug in 3, you end up getting 8, because 3 squared is 9 minus 1 gets me 8. So I'm only interested in this function on this specific closed interval. All right, so let me sketch the graph here. So on the closed interval, this is what f of x is equal to x squared minus 1 looks like. And so if you look here, what you're going to look is you're going to look at the function. And it's just like, okay, where's the maximum value the function takes on? And so it looks like right here, this value 8 is the maximum function, or maximum value. Okay, and so this is the point 3, 8. So what we then say here, okay, is we can say that f of x has a maximum which occurs at this point here, 3, 8. So there's a maximum of the function, and it occurs at the point 3, 8, because that's the highest value that the function can take on. And then look, if you look at the graph, like where's the low point, right? And it looks like it's right here, at this vertex of the parabola here. So this is the minimum value here, okay? And this occurs at the point 0, -1. So what we can also say then is f of x, the function, has a minimum which occurs at this point 0, -1. So really what this is, another way of saying this is the minimum value on this closed interval, and I'm just going to do it for the minimum, not for the maximum here, this other verbiage, but the min of f of x on the interval from closed interval from -2 to 3 is -1, which occurs at x is equal to 0. So that's a little wordy. So sometimes, what I'll just be saying is f of x has a minimum which occurs at that point. And that point tells me the x value, it occurs at x is equal to 0. And then it tells me the corresponding minimum value, which is -1. But again here, all we're doing is we're looking at the graph, and we're saying, okay, where's the maximum value the graph takes on? Where's the minimum value? And those are called the extrema. So I hope this visual now kind of helps it make sense when I talk about maximum and minimum values that a function can take on. All right, so let's expand on this now, okay? Let's expand on this and talk about what happens if it's an open interval. Okay, so I'm going to do the same problem. So I'm going to go to the next slide here. So let's consider f of x is equal to x squared minus 1 on the interval. So over here, going back, we did it from closed interval -2 to 3. So here we're going to do it on the open interval from -2 to 3. So note it's an open interval. What that's telling me here is you don't actually include the endpoints here. All right, so just like over here, what I'm going to do is I'm going to find the extrema here on the open interval. So again, I'm gonna sketch the graph here. All right. Now, what you're going to notice here when I plug in -2. There's going to have to be an open circle here, okay? And then when I plug in 3, there has to be an open circle here. So when I sketch this graph, it looks like this. It looks the same thing, but there's open circles at the endpoints here. So when you have when I would say this, I would look at this, I'd say like, well, what is the maximum value here? Well, it can't be 8 because there's a hole in it, right? So then what is the maximum value? Is it 7.99? Is it 7.99? Is it 7.99? Is it 7.99999? Like there's no 7.9 whatever that you can state that is the highest value. So when you have a max and it looks like it's butting up against an open circle here, what we say is this function has no maximum on the open interval. And that's okay. All right, and that's because there's no value. It looks like it's going to 8, but the function actually isn't 8. Okay, there's a hole in the graph here. But we can still say there's a minimum. Like you can look at this and say definitively there's still a minimum here. So f of x has a minimum, all right, a min value. Okay, so here has a minimum min value which occurs at still at that point 0, -1. So what I'm hitting at here is when you have an open interval, you cannot have max or min values at the end values of the interval. So I'm just gonna note that for you. When you have an open interval, no max min can occur at endpoints of the interval. Okay, very, very, very important to note there. All right, so now we've looked at here, we've looked at extrema on a closed interval. Now we've looked at extrema on an open interval. Now I want to talk about a really important concept called relative extrema. All right, and this concept of relative extrema will make more sense again when I do the visuals on the next slide, okay? So you're going to consider some function f of x, all right? And now if there's an open interval containing c, so you get to define the interval here, okay? So but then what we're going to say is on which f of c is a maximum, then f of c is called a relative max of f, right? Or you can say that f has a relative maximum at c f of c. So it's relative to the values around it, okay? So relative to the values around it. So relative to values close by, and this will make more sense when I do the first visual. And so if there's an open interval containing c on which f of c is a minimum, then f of c is called a relative minimum f, and you can say f has a relative minimum at c f of c. Okay, so again, relative minimum, just it's relative to values close by. And so what you're going to notice is you're going to notice relative max occur at peaks in a graph. So they occur at a peak in the graph. And then these relative mins, which you're going to notice when I do the first visual, is they're going to occur at a valley in the graph. Okay, so relative max occur at peaks, and relative mins occur at valleys. Okay, so the plural of relative maximum of a relative max is relative maxima, and the plural of relative minimum is relative minimum is relative minima. Okay, relative max and relative mins are sometimes called, because they're relative to values close by, local max and local min respectively. Okay, let me show you a visual of this to have this make more sense for you. Okay, so in each of these, what I want to do is I want to find the relative extrema. All right, so I'm going to do a graph that first looks like this. So this graph is going to go, I'm going to pick some points here. Suppose the graph looks like this. Okay, just something like this. All right, let's look at this first turning point here. Look, if you were to define just an interval around it, around this point here, and this is the point negative 4, 4. Okay? Negative 4, 4. Relative to the points just around it, we would say this is a minimum value, a relative min. Okay? Because it occurs at this valley. So just looking at this, we have a relative min. We have our first one occurs at negative 4, 4. Okay, just relative to values around it. But then look, up here we're at a peak. And so this right here looks like a maximum value relative to values around it. Again, it's not the maximum value of the function, right? Over here, I should do this. I should make this turn here. Let me apologize and make it turn like this so it makes more sense here. Like this is not the minimum value of the entire function, right? Because the function goes down. Sorry, I should have had it turn there. So this peak up here, which occurs at the point negative 2, 7, relative to the values around it, it is a maximum. All right, and then here, look, we have another turning point here, another valley. Okay, and this is the point 0, 4. So relative to the points around it, it's a minimum value. So we have another minimum at 0, 4. And then we have another peak here. Again, it's not the maximum value of the function because the function keeps going up and up and up and up and up. But this is the point 3, 8. And what we can say here is, that's a relative max here to the values around it. Notice the values 7 and 8 are different, right? Like, whereas the minimum values of 4 and 4 are the same here. But that's okay, because it's just relative to the values around it. It's just like a local maximum here. So you can have different y values here. All right, let's look at one more graph here and show the relative max and relative min. So maybe just have a graph that just looks like this. Well, look, you can see here, I have this peak. All right, relative to the values around it, it's a maximum. The graph goes up and up forever, so it's not like a global max here, okay? So this is the point negative 3, 4. So relative, we're at this peak in the graph. We have a relative max, which occurs at minus 3, 4. And then look, we have this little valley here. This is the point 2, negative 2. And relative to the values around it, again, the function keeps going down. It decreases without bounds, so it goes down forever. But relative to the values just around it, we have a relative min. Okay, so you're looking for these local peaks and local valleys to help you identify where you have relative extrema. Okay, so what I want to do now is, it's one thing to just look at the graph and figure it out. But now what we want to do is we want to apply the calculus to it. So like, where do we notice, what do we notice about relative extrema? Well, if you look at the tangent line, okay, at these peaks and valleys, look, the tangent line of each of these is a horizontal line. So just an important note here. Note, the tangent line at these extrema have a slope of 0. All right. Well, what gives the slope of the tangent line? Well, it's the derivative. So you can find these. You can find these by looking where the derivative is equal to 0. And that brings us to what we call critical values or critical numbers. I'll interchange those words, but they're going to mean the same thing. So the definition of a critical number here. So let's let f be defined. So the function is defined at c. If f prime of c is equal to 0, or if f is not differentiable at c, then what we say is c is a critical number of f. Okay? So this c is where when f prime of c, so we're plugging in c into the derivative, is equal to 0, what this means, the slope of the tangent line is 0, is the slope of tangent line is 0. So we have a horizontal tangent line. Well, what that means, when we have a horizontal tangent line, these horizontal tangent lines are only going to occur at valleys or peaks. Okay, so they only happen at peaks and valleys. What that means is that this here, this x is equal to c, is where a extrema occurs. And that leads us here is the theorem 4.2 here is that relative extrema occur only at critical numbers. So if f has a relative min or relative max at x is equal to c, then c is a critical number of f. And look, boom, you found a procedure to help you find your relative extrema here. All right. So this is going to lead us now that we have, and this will make more sense, I promise, these concepts here will make more sense when I work through the next couple examples. What we're going to now introduce is, using this concept here, is a procedure for finding extrema on a closed interval. And what I'm going to do here is I'm going to rework these steps here, and I'm going to go back for a second, with this example right here. So I want to find the extrema on this closed interval of f of x is equal to x squared minus 1 on this closed interval from -2 to 3. All right, so to find extrema of a continuous function f on a closed interval from a to b, we're going to use these following steps. All right. First thing we're going to do is we're going to find the critical numbers of f in the open interval a to b. Then what we're going to do is you're going to notice I'm going to do these next two steps simultaneously. So what I'm going to do is I'm going to evaluate f at each critical number that I just found in that open interval to a to b. But then even just looking back real quick, we saw here that an extreme value occurred at an endpoint of the interval. So then what you're going to have to do is you're going to evaluate the function f at each endpoint in that closed interval a to b. So you're going to have to evaluate it at a and b. And then the least of these values is the minimum, and the greatest of these values is the maximum. Okay. So look, how do you find critical numbers again? This first step 1. Find f prime of x. Set f prime equal to 0 and solve. That solution to f prime of x is equal to 0. You're going to get something like x is equal to c, a solution here, is a critical number. Okay, that means that critical number that tells me that you're either at a peak or you're at a valley. Okay. So again, what we're going to do, we're going to consider this function, f of x is equal to x squared minus 1 on this closed interval -2 to 3. All right, so let's find the absolute extrema of the function on this closed interval. So let's look at f of x is equal to x squared minus 1 on the interval -2 to 3. Okay, so the first thing you have to do is you have to find the derivative. Okay. Find f prime of x. Well, that's really easy. This derivative here, the derivative of this, it just ends up being 2x. Now what you're going to do, now set f prime of x equal to 0 and solve. So f prime of x is equal to 2x. Set that equal to 0 and solve. It's pretty straightforward, right? You just divide by 2 and you get x is equal to 0. And this is a critical number. Now look, you say, okay, x is equal to 0. That's inside the interval. Okay, so I'm gonna have to take this value and plug it into this function here. So now you're gonna evaluate the critical numbers you found and then the endpoints of the interval. So now you're gonna evaluate f of x at the endpoints, -2, the critical value, and then the other endpoint, 3. -2, 0, and 3. So f of -2. That's -2 squared minus 1. That's 4 minus 1. That gets me 3. F of 0, well, that's 0 squared minus 1. That gets me -1. And then f of 3, well, that's 3 squared minus 1. That gets me 8. And look, this is what we do. The least of these values is the minimum. Well, -1 is the minimum value. And the greatest of these values is the maximum. So boom, this is our max right here. So going back, this is what's going to happen. Okay. We saw that we have a maximum value at 3, 8, and that's exactly what we see here. Okay. We have a maximum which occurs at, well, this value, well, the x value is 3, the y value is 8. And then we have a minimum value I added the value here, which occurs at this point here, 0, -1, which is exactly what we found when we split this up and looked at the graph. So now we did it with the actual calculus of it. Okay, so you could hopefully see the procedure here, right? Find the derivative, set it equal to 0. That finds the critical numbers, and then you're going to evaluate the function here at x is at the endpoints and at the critical numbers. All right, so then what we want to do now. Now I just want to do, I've got a number of other examples picked out. So we'll start with easier ones, and then we'll work our way to harder ones here. Okay, so we'll do another polynomial one here. Okay, so let's consider this function. F of x is equal to x cubed minus 3/2 x squared. And what I want to look for is I want to find the extrema on this interval, closed interval, from -1 to 2. All right, so hopefully you can see the procedure. I'm going to find the derivative. F prime of x. Well, the 3 comes down. Minus 3/2. Bring the 2 down. Times 2. And then x. Well, just cleaning this up, the 2's cancel. And I'm left with 3x squared minus 3x. All right, that's my derivative. Now you're going to take this and you're going to set it equal to 0 and solve. So f prime of x here, which is 3x squared minus 3x, I'm going to have to set it equal to 0 and solve. Well, look, how am I going to solve this, right? I'm going to factor out a 3x, and I'm left with x minus 1. And you can see here that 3x has to be equal to 0, or x minus 1 has to be equal to 0. So one critical number is 0, and another critical number is 1. Okay, so I found the critical numbers. So look, 0 and 1, they both occur in this interval. So now all I have to do is I have to evaluate this f of x for -1, and then my critical numbers, 0 and 1, and then the other endpoint, 2. So at this point now it just becomes, unfortunately, a little bit of arithmetic, right? So f of -1, well, that's -1 cubed minus 3/2 times -1. squared. Well, negative 1 cubed is negative 1. Negative 1 squared is 1. So this is just minus 3 halves. So you change this to 2 over 2. So you get minus 2 minus 3. You get minus 5 over 2. F of 0. Well, that's 0 cubed minus 3 halves times 0 squared. Well, this is easy, right? This is just 0 minus 0. So that's 0. F of 1. This is 1 cubed minus 3 halves times 1 squared. Well, this is just 1 minus 3 halves. So you make this 2 over 2, and you get minus 1 half. And then just f of 2. Well, this is 2 cubed minus 3 halves times 2 squared. Well, this ends up being 8 minus 3 halves times 4. Well, 3 times 4 is 12. Divided by 2 is 6. 8 minus 6, this just ends up being 2. So look, what is the minimum value of all this? This is our min, and 2 is our max. Yeah. So it just worked out that the extrema here occurred at the endpoints, and that's okay. So we have a maximum, which occurs at this value here, 2 comma 2, and then we have a minimum which occurs at this value here, negative 1 minus 5 halves. Okay. So we've done some polynomial functions here. Okay, so let's expand on this now. We'll do a rational function, we'll do a trigonometric function, and then we'll do a one that involves e and a trig function. So we'll make them a little bit harder here. All right, so here will be the next one. Okay. So now let's consider this function. Let's look at f of x is equal to 6x squared all over x minus 2, and we want to look on the closed interval from negative 2 to 1. Okay, so you're going to need the quotient rule here, right? Unfortunately. So f prime of x. So you take the derivative of the numerator, which ends up being 12x, times the denominator, which is x minus 2, minus the numerator, which is 6x squared, times the derivative of the denominator, which is just 1, all over the denominator squared, which is x minus 2 squared. So you have to clean this up. So distribute here, you get 12x squared minus 24x minus 6x squared, all over x minus 2 squared. Well, look, 12x squared minus 6x squared, this just gets you 6x squared minus 24x all over x minus 2 squared. So what you're going to have to do here, okay, you're going to have to set this equal to 0 and solve, okay? So this is our derivative. So when you do that, think of this as 0 over 1. Like, you're going to cross multiply here, right? So you're just going to get, really, when you have these rational expressions, the only thing you're interested in is the numerator equals 0. We see that we plug in 2, we get a divide by 0, but notice how 2 is outside our interval, so we don't need to worry about that situation. So really, you're just looking, where does 6x squared minus 24x equal 0? Right, so factor out of 6x. You're left with x minus 4 is equal to 0. So you have 6x equal to 0, or you have x minus 4 is equal to 0. So one number is x is equal to 0, and another one is x is equal to 4. But look, notice over here, 4 is outside our interval that we're interested in. So since this is outside, it's outside of our interval -2 to 1, we don't need to test it. We don't need to plug it in. We don't need to evaluate f of x for it. Okay, that's good. That means then we really only have to evaluate for 3 numbers: -2, 0, and 1. Okay, so what I'm going to do now is I'm going to go to the next slide here and plug those values in so you can see how it's solved. So again, our function was f of x is equal to 6x squared over x minus 2. And what we need to do is we need to evaluate for x is equal to -2, 0, and 1. So f of -2. This becomes 6 times -2 squared all over -2 minus 2. Well, this becomes 6 times 4 all over -4. Well, the 4's cancel here, and you're just left with -6. F of 0, that's 6 times 0 squared over 0 minus 2. Well, that's just 0 over -2, which is 0. And then f of 1, this is 6 times 1 squared over 1 minus 2. Okay, well, what is this? This is 1 squared is 1. This is 6 over -1, which gets you -6. So look, do you notice how you have the same -6 value? That's perfectly okay. So we actually have, excuse me, we have our minimum value is -6, but it occurs at 2 different points. So minimum, which occurs at 2 points, and that's okay. The first one is -2, -6, and 1, -6. That's okay, perfectly okay. And then we have a maximum, which occurs at just this point, 0, 0. All right, so a lot went on there. So again, if you solve and you get a value outside the interval, you don't need to test for it. Okay, let's do a trig one. We'll do a trig one here now. All right, and I have over here the graphs to help us why this is cosine of x and this is sine of x, just for your own reference to help you here. All right, so let's find the extrema for f of x is equal to -1/2 times cosine of 2x on this interval, 0 to 2 pi. Okay, so again, I have to find the derivative. So f prime of x is equal to, keep that -1/2. You're going to have to chain rule this. The derivative of cosine is negative sine of 2x. And then the derivative of 2x is 2. All right, so we'll look what happens here. This really worked out really nicely. Okay, negative cancel, 1/2, 2. Our derivative here is just sine of 2x. All right, so you have to look. This is where it gets a little tricky. You have to remember your pre-calculus here. Okay, you have to remember your pre-calculus here. So you have to look now. You have to find where sine of 2x is equal to 0 on the interval from 0 to 2 pi. Well, look, this 2 shrinks the period here, right? So look, here's sine. We see here that sine is equal to 0. This is just sine of x at 0, pi, and 2 pi. Okay, but what's going to happen here is the 2 is going to shrink it. So it's going to be 2x is equal to 0, or when does 2x equal pi, or when does 2x equal 2 pi. Well, you see here that those solutions end up being 0, pi over 2, and pi. So what you can see here is you're getting 0 every pi over 2. So you're also going to need to check. It's also actually going to happen at 3 pi over 2. Okay, so there's a lot of things you need to test now. You need to test 0, pi over 2, pi, 3 pi over 2, and 2 pi. So there's 5 values here. All right, so let me go to the next slide here. So we need to evaluate our f of x, which was equal to minus 1/2 cosine of 2x for x is equal to 0, pi over 2, pi, 3 pi over 2, and then 2 pi. All right, let's go through it. F of 0. Well, this is minus 1/2 times cosine 2 times 0, 2x, when x is equal to 0 is cosine of 0. Well, cosine of 0 is 1, so this is minus 1/2 times 1, which is minus 1/2. F of pi over 2. This is minus 1/2 cosine. Well, 2 times pi over 2 is pi. Cosine of pi, so you can, that's why I have it over here. Cosine of pi is negative 1. So this is minus 1/2 times minus 1, which gets me 1/2. And then, you have to keep going, right? So f of pi, this is minus 1/2, and this ends up being cosine of 2 times pi, because you have 2x in there, 2 pi. So this is minus 1/2. Cosine of 2 pi, boom, is 1. So you can see it's going to start, it's basically, it's going to oscillate here, right? So f of 3 pi over 2, this ends up being negative 1/2 cosine of 3 pi, which is negative 1/2 times negative 1, which is 1/2. And then finally, 2 pi. Well, when you plug 2 pi into 2x, you get negative 1/2 cosine. This ends up being a 4 pi. And cosine of 4 pi is just 1, right? So this is minus 1/2 times 1, which is minus 1/2. So look, you have max here, in here, and then you have min here, and min here. They're all the same. So you have maximum, which occur at, looks like it's going to occur literally at 2 different points, right? So the first point is pi over 2, 1/2. And the second point here is 3 pi over 2, 1/2. And then it looks like you have minimum, which occurs at so you have 3 points here. You have 0, negative 1/2. You have pi, negative 1/2. And then finally you have 2 pi, negative 1/2. All right, so that one was a bit tricky. All right. So let's do one last one. Okay, it'll be a little bit of trick. So let's find, be our last one here. The extrema of f of x is equal to e to the x times sine of x, just on the interval from 0 to pi. Okay, so tricky here. So first you're going to find the derivative, right? You're going to have to use a product rule. So derivative of e to the x is e to the x times sine of x plus e to the x, and then derivative of sine of x is cosine of x. So now you have to set this equal to 0 and solve. So you have e to the x sine of x plus e to the x cosine of x equals 0. Factor out an e to the x. So you have two things here. You can have either e to the x is equal to 0 or sine of x plus cosine of x is equal to 0. Well, here this doesn't happen. Okay, this you can't solve this, right? No solution here. Well, over here, I'm going to just subtract the cosine over it. I have to look, where does sine of x equal negative cosine of x? Specifically from 0 to pi. So here's cosine from 0 to pi. Okay, and this is sine from 0 to pi. Well, look here. Somewhere between pi over 2 and pi, they're opposite signs, right? So somewhere between there, sine is positive and cosine is negative. Well, so if you take the negative of it, right, that they would be the same value. And so, you know, if you remember your trig, this will happen on this interval when x is equal to 3 pi over 4. All right, so you're just going to have to test. So now evaluate f of x for x is equal to 0, 3 pi over 4, and pi. So this is my f of x here. Okay, so for 0, f of 0, well, that's e to the 0 times sine of 0. Well, that's, you know, e to the 0 is 1, sine of 0 is 0, so that's just 0. F of 3 pi over 4. All right, well, that's e to the 3 pi over 4 times sine of 3 pi over 4. Well, sine of 3 pi over 4, hopefully we remember, that's square root of 2 over 2. So I'm going to change this as square root of 2 over 2 times e to the 3 pi over 4. And then f of pi, well, that's e to the pi times sine of pi. Well, you know, like what is sine of pi? That's 0. So look, we have a minimum value of 0, which occurs at 0 and pi. So we have minimum, which occurs at, we have this 0, comma 0, and at pi, comma 0. And then we have a max, which occurs at this 3 pi over 4, and then the resulting value is square root of 2 over 2 e to the 3 pi over 4. All right, class, a lot of examples here. You know, and I promise the more you practice this, the easier it will get in the coming, you know, in the coming lectures. And so as always, if you have any questions, you know, please let me know.